Hi everyone. I'm making this video so that you guys can get up to speed on a few kind of eclectic, weird topics that you're going to need because with COVID-19 kind of knocking your education around, I've tried to limit the damage by looking for units that we can teach remotely that don't have very many practical components. So I don't want you guys to miss out on any experiments. So while I was preparing some lessons for my 6th years, I noticed that the last kind of 3 chapters or so are very cognitively demanding. Would say they're going to need to think, but they lend themselves well to being taught at a distance. It doesn't really matter too much that we're not in the classroom for these ones. Now the only problem is to get to those 3 units. There's a few different concepts you're going to need if they're going to make any sense to you. So that's the purpose of this video is. So there's three things really to say here. First is it's a bit eclectic. It's a bit all over the show. It'll jump from topic to topic. And for each of these, we're just kind of skimming the surface of each bit. So when we get to it properly, when we're going to do it, looking at magnetism, electricity, we'll be doing it in a lot more detail. But this is just kind of the detail knowledge you're going to need. And even though, that being said, some of it is actually quite tricky. So hopefully you're up for it. Let's give it a shot. We're going to start by having a look at the nature of charge. And I'm going to start by very simple kind of explanation or a very simple demonstration. Like if you rub a balloon against your jumper or your clothes, you'll find that you can make it stick to a wall. And I'm going to try and explain why that happens. So first thing you need to be familiar with is charge comes in kind of two flavors. There's positive charge and there's negative charge. If they're opposites, if you have a positive charge and a negative charge, they're going to be attracted to each other. But if they're the same type of charge, if you've got two negatives, they won't be attracted to each other. Instead, they're going to repel or push against each other. And the same for two positives as well. They're going to push against each other, they're going to repel. Okay, so the nature of these charges. Well, first off, it kind of comes from the structure of atoms that are making up everything around you, including you. So you've got the basic structure of the atoms. You've got the positive nucleus, I beg your pardon, in the center, because that's where the protons are with the positive charge. And they're surrounded by the electrons going around the outside of the atom with the negative charge. So you've got positive nuclei and you've got negative electrons. Okay, so how does this relate to our rub a balloon and stick it to the wall example? Okay, well here's a diagram of a balloon. I've got the red dots are meant to represent the nuclei of the atoms that make up the balloon. Now, I've drawn only a handful here. Obviously, there's billions upon billions upon billions in real life, but a bit impractical to draw. And even though it looks like they're filling the balloon in this case, remember this is just the surface of the balloon, the outside of it. Okay, so each red dot is a nuclei, and they're positive. They've got a positive charge. And they'll also have electrons with a negative charge. And the key here is there's an equal amount of positive and negative charges. So overall, the balloon will be neutral, like all other neutral matter that is everywhere. You've got an equal amount of positive as you do negative charge. But if you want to give it a charge, you can do so quite easily. If you rub it against, let's say, your jumper or some clothing, there's two kind of scenarios that can happen. So the first one is, let's say that the balloon's going to get a negative charge. So if you rub it against your jumper and extra electrons are transferred from the jumper onto your balloon, then the balloon is going to have a net negative charge. Now it could happen the other way around, depending on your clothing and the materials. Instead of the electrons being transferred onto the balloon, you can actually sometimes get electrons, the object. You can also sometimes get electrons transferred off of the object. In this case, if we rub it against a different type of clothing, or if the balloon's made of different materials, electrons could be transferred from the balloon onto your jumper, leaving a net positive charge behind on the balloon because you've still got all those positive nuclei, but now you've got less electrons. Now that second scenario is just there to illustrate it can happen both ways. Now in terms of balloons, it's the first one, it's electrons getting transferred. So we're going to have a look at that and what happens next when you move it next to a wall. Okay, let's start by looking at the kind of first scenario. We've got a negatively charged object like this balloon, and we're going to move it close to the wall and see what happens. Okay, so remember the balloon's got a net negative charge. It's got more negatives than it does positives. And the wall, here's a diagram of the wall, it's also made up of nuclei, which are positive, and they each also have electrons, which are negative. And again, in its neutral state, the wall is just balanced, equal number of positive and negative charges. Okay, so as we bring the balloon closer to the wall, remembering that the balloon is negatively charged, remembering that like charges repel, the negative charge on the balloon will push away the negative charges on the wall. It'll push them away from the balloon. And what that does is it leaves a kind of a localized area near the balloon of positive charge. So the part of the wall nearest the balloon will now be positive because the negative has been pushed away. And now you've got that positive part of the wall and the negative balloon. Because they're oppositely charged, they're going to be attracted to each other. And this force of attraction is enough to kind of make them stick together against gravity, which is trying to pull the balloon down and separate them. Okay, and if for some reason the balloon had a positive charge, it would work in a very similar way, that when you bring it close to the wall, the positive charge in the balloon will push away the wall's positive charges. Another way of looking at it is that it brings the negative charges of the wall closer, kind of drags the electrons over, which will leave you with a negative charged part of the wall near the balloon, and the further away will be positive, but that negatively charged area of the wall will be attracted to the positively charged area of the balloon. So regardless of whether you're talking about positive or negative charge, the unit is the coulomb, and having a charge is caused by the movement of electrons. Either something will gain electrons and get a negative charge, or it will lose electrons and get a positive charge. An electric field is an area where if you put in a static charge, it's going to experience a force. So the convention is we use these lines to represent it. And what it means is if I was to drop a static charge, like a positive or a negative charge in here, it would go in a certain direction. It would experience a force and it'll be pushed or pulled by the electric field. So the convention is the arrows show the direction that a positive charge would take if it was placed in the field. So the positive charge would be pushed in that direction. Now, you can probably imagine that if a negative charge was put in, it would obviously go in the opposite direction. Okay, this is just a convention, but it's an important one that you have to be aware of. Okay, so potential difference. You've probably heard of voltage, or in terms of batteries and stuff. Voltage is a measure of the potential difference. What it means is how much work would have to be done to bring a coulomb of charge from one point to another in an electric field. So imagine, let's say that you were trying to push a positive charge against the direction it wants to go. That's going to take energy. So voltage is a measure of how much energy that would take. And its unit is the volt, but it's also known as the joules per coulomb. So how much energy you need to bring a coulomb of charge. Another convention that's going to be important is when you're drawing vectors. So we know that a vector has both a magnitude and a direction. And because we're trying to represent 3D things in 2 dimensions, on paper and on screens and stuff, it's a little tricky. So we need an extra convention. So sometimes the vector is going to be coming out of the screen towards you or going into the screen away from you. And we need to have an easy way to describe what's happening in each one. So to do this, remember that a vector is an arrow. And I want you to think of an arrow that you actually shoot from a bow, like this one. Or more specifically, the one that Rambo uses in Rocky, that Rambo uses in Rambo, as he does. The kind of conical shaped one. It's a little easier to get your head around. Not literally, hopefully. So if there's an arrow flying towards you, it would look a little like the one on the right there, with a dot in the center and a circle around the outside, as though the top of that cone is flying towards you. And if it's gone past you, or it's just narrowly missed you, it's going past, you'd look back and you'd see the kind of feathers sticking out to each side, the fletching. And it would look a little like that crosshairs. So the convention is if a vector is coming out of the screen or the page towards you, it'll be a dot with a circle around it. And if it's going into the page away from you, it'll be a circle with those kind of 4 lines going across each other. The next item on the physics smorgasbord is magnets. I'm hoping that you'll have a bit of a go with magnets at some point, either in primary or in junior cert. But again, we'll go into this in a lot more detail ourselves when we get to the unit property. But for now, magnets generally made of one of iron, nickel, cobalt, or alloys of them. So I've taken a block of iron here as an example. So basically, it's something that can be magnetized, something that can be made into a magnet. What's that actually mean? That means that if you form something into a magnet, it's going to have 2 poles, a north pole and a south pole. I've colored them red and blue respectively here, but I don't know if that's a convention or if it's just the way I'm used to doing it. But anyway, so you got a north and a south pole. And in a similar way to how the charges that are alike will repel, the same thing happens with poles. 2 poles that are the same will repel each other. 2 north poles will repel, and 2 south poles will repel. And the opposites will attract. So if you've ever had to play with magnets, you know yourself, trying to push 2 of the same together, it's quite difficult to do. Whereas if they're opposites, they're going to snap together quite quickly. So again, we need to represent this. We do so with a magnetic field. And again, it's quite similar to how we represent an electric field. This time, the arrows indicate what would happen if we dropped in a north pole. What direction would it move in? So the arrows are going to join then the north to the south pole of the magnet, because that's what would happen if I dropped in another north pole. It would get pushed away. So again, it's another convention that we need to be aware of. All right, the final topic we're going to end with is probably the trickiest. It's called Fleming's left-hand rule. Now, a little bit of context here. What it refers to is figuring out if a charged particle moves through a magnetic field, it will experience a force. Fleming's left-hand rule lets you predict what direction it's going to go in. So one more time, a charged particle moving in a magnetic field is going to experience a force, and we need to find out which direction it's going to go. Okay, well first off, let's start with a magnetic field. So here we've got a north pole and a south pole, and the field lines that join them, again showing what would happen to a north pole. So it's going from the north to the south pole. Now a neutral particle that passes through won't be affected at all. If it will keep moving at whatever speed it was moving at before, go right through the magnetic field, not a bother, no problem. But a charged particle won't. A charged particle is going to be deflected somehow. So for example, we're going to start, let's have a look at this positive charge. So as the positive charge moves into the field, something strange happens. It experiences a force, and it's quite hard to represent here, but I've tried to draw it smaller and smaller. It's actually getting pushed away into the screen, away from you. Whereas a negative one, moving in the same direction at the start in the same magnetic field, goes in the opposite direction. This one's going to be deflected out of the screen towards you. Again, I've tried to illustrate that by having it get bigger towards the camera. So let's have a look at how Fleming's left-hand rule actually works. This is a little bit tricky. Let's give it a go. So we'll stick with the example we were working with before. We've got a north pole on the top of the page and a south pole on the bottom. Remember, you could organize this in any way. I just chose having a north pole and a south pole. Remember, you're dealing in 3 dimensions, and that's why we need Fleming's left-hand rule. Okay, so let's say we've got a particle moving from the left hand side of the screen into the field. All right, well, first thing I want you to do, this is my hand, obviously. We're going to go with the thumb. You're going to need your first 3 fingers, so your thumb, your first finger, and your second. What I want you to do is, first off, kind of like make a gun. Make a kind of classic gun face shaped thing. And then I want you to stick your second finger out. So basically, you want to end up with all 3 of your first fingers are 90 degrees to each other. So if it looks like you're doing the lamest gang sign in the world, you're doing it right. So your thumb sticking up the top, your first finger sticking out like a little gun, and then the second finger, it'll probably be pointing towards you. Then you're doing it right. Okay, so how does this work? Well, first off, we're going to use the T is for thumb, the F is for your first finger, and the C is for your second finger. It's the best we can do. So first thing we're going to do is your first finger, I want you to align it with a magnetic field pointing from north to south. So that's going to align with the field. F for field, F for first. The second finger, which for whatever reason we're going to call it C, that's going to align with the current, the movement of the charged particle. And it's going in the direction that the positive charge is going. So in this case, it's going to the right. Now, if we've done it right, the T for thruster, your thumb, is going to show you the direction that the force is going to act in. So let's kind of recap that. There's a particle, a positively charged particle, moving from left to right. We aligned our first finger for field with going from north to south. Our second finger is going in the direction that the positive charge is going in, so that was going from left to right. And that meant that our thumb, if we've done this correctly, it should be pushing into the page. It should be kind of going away from you. When you're aligning the second finger for the current, remember that it's the direction that a positive charge would move. So if you're dealing with a negative charge, you have to go in the opposite direction. And then Fleming's left-hand rule will still be valid and still apply. Okay, so Fleming's left-hand rule, if we could just recap why we did all that, will tell us what direction a charged particle will move in if it's in a magnetic field. Now that tells us the direction it's going to go, but remember we're dealing with a vector, so we have the direction. What about the magnitude? Okay, it turns out the magnitude is quite easy to calculate. The force that it's going to experience, the magnitude of the force, is this Q by V by B. Let's look at them one by one. Well, the Q is the charge, so the more charge, the more force it's going to experience. V is the speed, the velocity at which it's moving. And again, the faster it's moving, the stronger the force is going to be. The only tricky one here is this B, which you haven't encountered yet. B is a measure of how strong the magnetic field is. How many of those magnetic field lines would be there. And it's measured in Teslas. So that's probably the trickiest kind of thing we dealt with today. Look, there's quite a lot to get your head around, especially in that Fleming's left-hand rule stuff. This is one part that's definitely not suited to teaching remotely. But unfortunately, it's the last hurdle before we get on to the good stuff. Well, almost the last hurdle. We've one last kind of concept to look at, and that is waves. And then afterwards, we're going to look at electromagnetic waves. So first off, when you think of waves, you probably think of waves just in the sea, right? And that is an example of a wave. But a kind of a more precise definition of what a wave is. So we're going to look at mechanical waves first. And a mechanical wave is basically just a way of transferring energy from one place to another. So it's a disturbance carrying energy through a medium without any overall motion of that medium. So for example, going back to our sea example, if you ever look at as waves pass underneath the boat will tend to go up and then down again. It isn't moved from side to side. There's two main types of waves. Longitudinal waves, which we're not really going to look at today, and transverse waves. Now, in a transverse wave, if the wave here is moving from left to right, the disturbance is at 90 degrees to the direction of movement. It goes perpendicular to the direction that the wave is traveling. Now, looking at some of the kind of keywords we're going to be using in terms of the anatomy of a wave, the wavelength is literally just how long is the wave. How long is it from one top of one wave to the top of the next one, or from the bottom of one wave to the bottom of the next one. We call these peaks and troughs. So you can measure from peak to peak or trough to trough, but the wavelength is just a distance measurement of how long the wave is, literally how long it is. And a little bit cut off in my diagram here, if you look at the height of a wave, that's referred to as the amplitude, so how much is the medium disturbed. So the height of the wave is measured from the center point to either a peak or a trough, and is known as the amplitude. The other kind of keyword we're going to look at is the frequency of a wave. And that just means how many of these waves pass you per second. So if you're standing at the one point and a wave passes you by, how many peaks or troughs will pass by in 1 second? So because of that, its unit is just per second, which is referred to as the hertz. So it's how many waves pass you in 1 second. Now finally, if you want to figure out the speed of a wave, what you've got to do is multiply the frequency by the wavelength. So how long is each wave and how many pass per second? If you want to think of a way to kind of imagine this easily, think of somebody running. If you're trying to improve your speed at running, you can do two things. You can either take bigger steps, so like a longer wavelength, or you can take more steps per second, so you can increase the frequency. Now, a really good runner will do both. So they'll take long strides and take more of them. So by increasing the frequency or the wavelength, you can increase the speed of a wave. And finally, you'll be very relieved to hear, we're going to look at electromagnetic waves as distinct from mechanical waves. So electromagnetic waves are a type of, you're probably most familiar with light as an example of an electromagnetic wave. And electromagnetic waves don't need a medium to travel through, so they can travel through a vacuum. They come in a whole range of different wavelengths and frequencies. We'll come on to the link between wavelength and frequency for electromagnetic waves in a moment. But just look at this diagram, look going from left to right, you're increasing wavelength. So on the very far left, you've got gamma rays with a very short wavelength and a very high frequency. So gamma rays are very energetic. They can be very damaging if you were to encounter them. In the same way, X-rays also have a very short wavelength but a high frequency, and these can also damage your cells if you were to encounter them. Which is why, for example, people doing X-rays who are doing the scan will often stand behind a big lead shield to protect themselves from it. Now, it doesn't matter too much if you're getting the occasional X-ray, but if you are exposed all the time, it can be very dangerous. Similarly, UV light wavelengths, we're kind of going in order of increasing wavelength here. So UV light can be damaging if you get too much of it. Then we encounter the visible light spectrum that we can see between ultraviolet and infrared, and again increasing wavelength. Then we're into infrared, microwaves, and then TV and radio waves. So all the time here we're talking about increasing wavelength and decreasing frequency. Here's a version of that same diagram, this time with the waves kind of shown at the top. So we're going from short wavelength to long wavelength, high frequency to low frequency, and just it's showing there the length of the waves as well in meters. And just on an aside, you can also draw it going in the other direction if you wanted to, going from long wavelength to short wavelength. So going from radio waves to microwaves, infrared, visible, where the frequency is increasing but the wavelength is decreasing. It's just kind of it doesn't matter which way you draw it as long as you're aware of the differences. Okay, let's get back to kind of the relationship between frequency and wavelength here. And this comes down to the fact that light has a set speed. Okay, we can't increase the speed of light. The speed of light is the speed of light. So what that means is if you increase the wavelength, the frequency is going to have to go down. Because if you remember, the velocity, which is a constant that can't change, is the frequency times the wavelength. So if you increase one of frequency or wavelength, the other of those two has to go down. Okay, it's not been an easy day for you, I'd say. Now, don't forget, we'll be checking in on the live lesson. So any questions you have, I'm sure there'll be lots because this is tricky stuff. We'll be talking about it in the live lesson. All right, but well done for staying with us, I'll talk to you soon.